Namaskar and a very good afternoon to you all. Myself, Dr. Manu Mehta. I'll be taking you through the basics of remote sensing. I'm working as a faculty and scientist in the Department of Photogrammetry and Remote Sensing Department, IIRS. So let's begin with, in order to collect any scientific information, we have two options with us. One is using in situ measurements, which we call field measurements. That is, we go to the ground or we go to the actual site, take the measurement for with the target itself. So we also call it as ground truth, and this is the best information which is available with us for that parameter. So we call it as ground truth or in situ measurements or field observations. The other option is we don't go to the site actually, and from a distance, we take the information, right? So this is called remote sensing. Formally, we define remote sensing as the science and art of obtaining information about three things: an object, for example, a building; area, for example, a mix of features like a city or a district or some agricultural field plus the surroundings, etc., or phenomena like rainfall or disaster, etc. So it's both science as well as art. Science because the gathering of information is based on scientific principles. It is an art because interpretation of the information depends on the skill of the interpreter. So it started as an art, but it's both science and art of obtaining information about an object, area, or phenomena, as I told you with the examples, through the analysis of data acquired by a sensor or a device which is not in physical contact with the same. Right? So this is remote sensing. Now the next question before us is, why should we do remote sensing? Why you all are sitting today in this class? What is the use of remote sensing? And when we know that ground truth option is also available, right? So why remote sensing? One of the major advantages is systematic data collection. For example, I sent 20 people to the ground to collect the samples of soil for, let's say, soil moisture assessment. Now, 20 people going to the ground may be doing 20 different type of samplings. Even if they are doing the same type of sampling, then also there can be 20 different types of errors in the data, right? So, whereas with remote sensing methods, you have a systematic data collection. The data gets collected in a systematic fashion, right? Click, click, click in certain paths and rows, etc. The another advantage associated with remote sensing is that today you have all seen Google Earth images where you can see 3D information also available for several places. So this information about three dimensions of real objects is also possible using stereo images through remote sensing process. Then repeatability is possible both in space and time. Suppose you want to collect the data of a particular area after, let's say, every 10 months or 10 weeks or 10 days or 10 hours. That's possible, right? Depending on which satellite and sensor you're looking for, which application you are catering to, right? So repeatability both in space and time is a possibility with remote sensing. Global coverage and synoptic coverage. This is also again very highly possible with remote sensing, which is difficult using ground truth measurements because that's point-based measurements and you need to employ a large amount of manpower and time. Sometimes it becomes the only solution. For example, there is a disaster and we want to collect the data. It's risky to risk the lives and to access the areas which have become inaccessible now. volcano eruption, etc. So that time, remote sensing becomes the only possible solution. Apart from this, the same information can be interpreted in different manners by application people of different sciences. For example, the same information can be interpreted differently by a water resource person, or by an agricultural person, or by an urban resource person, or by a photogrammetrist, etc. Right? So there are several. You can, this list is not complete. You can complete the list yourself and look at what advantages do remote sensing offer over ground measurements. However, is it all? So should I stop going to the ground and collect the field information? No. Why? Because first of all, before we launch any sensor on a remote sensing platform, it has to be first calibrated with respect to ground measurements. So for calibration, we require ground measurements, of course. Also, once we receive the remote sensing data, we analyze it, we come to a conclusion. We need to assess how accurate the analysis is, how accurate the results are. So for accuracy assessment, or in other words, we can call it as validation purpose, we are still dependent on remote sensing. In fact, we can put it in this way. It won't be wrong if you put it in this way, that as long as remote sensing survives, the ground truth information has to survive, both for calibration as well as for validation. So apart from that, there are certain applications which are still the area of research for remote sensing and upcoming areas of research, for example, subsurface analysis, where we are still more relying on ground truth measurements. So now we have understood what is remote sensing, what are the advantages of remote sensing, that is, why at all should we go for it. Now the next part is very important, that is, how should we go about it? How, or what is the process of remote sensing? So what we need is, first of all, we require a source of energy. Okay, this can be a natural source, it can be an artificial source, but it has to be a source. In this example, I have taken sun as the natural source of energy for Earth. Second, you require a target. Here I have taken Earth observation. So Earth targets can be taken. You can go for extraterrestrial purpose also. And then, because Earth is surrounded by a layer of atmosphere, so this denotes the atmospheric cover. So it has the light which is coming from the source has to interact to the atmosphere and along with the target. Part of it from the target in this example is shown as being reflected by the target. Now this reflected energy goes to the sensor, which is sensing, or which is the remote sensor, which is sensing the information from the target. This sensor has to be kept on a stable platform. So it's a combination of sensor as well as platform. The details will be covered in the next class tomorrow for sensors and platform. Then the data which is captured on sensor is disseminated to the ground. That means you have a ground receiving station which consists of antennas as well as the associated electronics. So this electronic transmission of the data happens from sensor to the ground receiving terminal. In India, we have this terminal at Shadnagar. Once the data is captured here at the ground receiving terminal, this is pre-processed. Pre-processing is done, number one, to free the data which is captured by the sensor from some pre-known errors. Okay. Number two, it has to be converted to some usable format, which are commonly used formats like GeoTIFF or HDF, etc., which are commonly used by the users. Okay. So here pre-processing, that means error removal. The known error removals, and the conversion to usable formats is being done here. Different levels of pre-processing can be applied to, depending on which level of the product you want from the PI. Once the data is pre-processed, it is then given to the user for applying on various applications. So this is an example where the light from a passive source means a natural source, is going to the target, and part of it is getting reflected by the target and being received on the sensor. Now, there can be another scenario. For example, you might be using a source on the sensor itself. The sensor might be using, along with the sensor on the platform, you might be having an artificial source of illumination. So your platform consists of two things in this case, a sensor as well as a source of illumination. So essentially it has to be artificial source of illumination. So light from this source of illumination goes to the target. Part of it is backscattered and received by the sensor again. Okay, so this kind of remote sensing is called active remote sensing when we are using a source on the platform. Whereas when there is no source on the platform which is illuminating the target, that means we are dependent on some natural sources or some other sources which are not carried by the platform. That's called passive remote sensing. So this red solid line is showing passive reflective remote sensing, whereas this blue dotted line is an example of active remote sensing. Another scenario can also be there. You see that the target here itself is becoming the source. How it's possible? Suppose we are dependent on emissions from the target. For example, everything in this universe above 0 Kelvin is emitting some amount of energy depending on its temperature and emission characteristics. So if the sensor is sensitive to those emitted wavelengths, then you can record that energy and do the remote sensing process. So this dotted red line is an example of emissive remote sensing. Thermal remote sensing, which you'll be learning in the subsequent classes, is an example of emissive remote sensing. So here, the requirement is the sensor should be sensitive to the emissions from the body or from the target. So here, the target itself is becoming the source. So this is also a kind of passive remote sensing because there is no utilization of any source from the platform. So both are shown as red, the passive remote sensing processes, whereas the solid one is reflective remote sensing, passive remote sensing, and the dotted line is emissive remote sensing, again, form of passive remote sensing. So this is all in all, broadly, the process of remote sensing, where you need a source, you need a target, you need a sensor plus platform, you need a ground receiving station, you need to pre-process the data, and then it can be given to the user. So we have learned broadly what, why, and how part of remote sensing. So going ahead, our focus will be on the properties of electromagnetic radiation, because these are the radiations which are interacting with the target and bringing us the information from the target. So we need to get acquainted with the properties of electromagnetic radiation. Other two topics which we will be discussing in the subsequent time will be interaction of radiation with target as well as the atmosphere. Right, so coming to electromagnetic radiation, all of us by this time, I hope, must be knowing what is electromagnetic radiation. There are two theories. One is the wave theory and other is the particle theory. Wave theory considers that electromagnetic energy is a continuous form of energy in the form of harmonic sinusoidal waves. waves of changing or oscillating electric as well as magnetic fields. And particle theory considers that this radiation is consisting of several discrete components or units, which we term as photons. And this is how the wave propagation looks like. E denotes electric field, M denotes magnetic field. I have not shown the vector components of it, but just the amplitudes. You can see that at each point, electric and magnetic fields are perpendicular to each other, as well as oscillating perpendicular to the direction of propagation. All right. So there are certain terms which are associated with wave theory, which will help you to understand certain radiometric quantities, which you'll subsequently learn. So for that, the highest point of the wave is called crest. The lowest point of the wave is called trough. The distance between any two identical points, any two consecutive identical points on the wave is wavelength. And frequency is the number of wavelengths which pass a particular point in a unit time. So these are the basic four quantities which you'll frequently come across in the wave theory of electromagnetic radiation. Now, how the wavelength and frequency are related to each other is using this relation. C is equal to lambda into nu, where lambda is the wavelength and nu is the frequency. And the product is equal to the speed of light. It's a constant. So we understand that frequency is inversely proportional to the wavelength of light. And in order to compute the energy of the wave, we have the relation where energy is directly proportional to the frequency. So using the above relation of C is equal to lambda nu, you get E is equal to hc by lambda. H is again a constant, which we term as Planck's constant. Right, so we understand two things from here, that higher is the wavelength, smaller is the frequency, as well as smaller will be the energy associated with the wave. All right, so why do we depend on electromagnetic energy only? Because this does not require a material medium for its propagation. And for most of the remote sensing, which is satellite based, we require the energy to propagate its maximum length, path length through vacuum. So it's possible only using electromagnetic radiation. That's why we discuss broadly electromagnetic radiation in remote sensing. Now, because in the beginning I discussed that there is a wave nature, there is a particle nature, but both are contrary to each other. So to bring them to the same platform, there is a hypothesis by de Broglie, who suggested that the momentum of the photon is inversely proportional to the wavelength of the wave. Okay, so here we are connecting two natures together, where lambda is the wavelength, we call it as de Broglie wavelength, and p is the momentum which is associated with the particle. Now, particle here is photon, which does not carry any mass. However, photon is still finite, momentum is still finite, whereas for a massless particle, momentum becomes zero. However, here in this case, we can compute the momentum using the de Broglie wavelength or wavelength of the wave, right? H is again the Planck's constant. So this equation connects both the wave as well as particle nature of light in one equation. Right. So knowing the previous concepts, we can arrange the entire electromagnetic spectrum in the order of wavelength or frequency or energy. Here I have arranged it in the order of increasing wavelength from left to right: cosmic rays, gamma rays, X-rays, UV, visible, IR, microwaves, and radio waves. The highlighted portion, the yellow highlighted portion here shows the part of electromagnetic spectrum which is widely used for Earth observation. So for Earth observation, we are more depending on visible IR and microwaves. Ultraviolet radiations are also used, especially for atmospheric remote sensing of the Earth. So you can see from cosmic rays to radio waves as we go along, we see that the wavelength starts increasing of the order of 10 to the power minus 18 meters to 100 meters or so. And consequently, frequency decreases from 10 to the power 26 hertz to 10 to the power 6 hertz. And subsequently, energy can also be seen to be decreasing as we go from cosmic rays to radio waves. Right. So, as I said, for Earth observation, or Earth target observation, we are more relying on visible IR and microwaves. So, let's see the wavelength span of this range, visible range, the light, which are eyes, that is our remote sensors, okay, that carrying with us, ranges from 0.4 to 0.7 micrometers. Infrared ranges from 0.7 to 100 micrometers. However, we have a further categorization of infrared radiation from 0.7 micrometers to 3 micrometers, which covers the reflective IRs, and from 3 micrometers to 100 micrometers, that falls under thermal IR. So as I had discussed in the beginning, so 0.7 to 3 micrometers, because most of the infrared radiation in this region gets reflected. So we perform reflective kind of remote sensing in this region. So, and 3 to 100 micrometers region, we have maximum emissions from Earth. So we call it as thermal IR. Here we can carry out emissive remote sensing, again, passive remote sensing. So 0.4 to 3 micrometers, that is visible plus reflective IR. This together forms optical range of remote sensing. The optical range is not only confined to visible, it includes visible plus reflective IR up to 3 micrometers. And thermal IR covers 3 to 100 micrometers. Then microwave range is followed after infrared radiation. So here the nomenclature is more frequently used in terms of frequency bands: P band, L band, S band, C, X, 2, K. These bands are millimeter and sub-millimeter bands. And the details of it would be covered in a separate class on microwave. It started gaining in popularity in the beginning because the longer wavelengths could penetrate the clouds and bring the information from the Earth target, which was not possible using optical remote sensing. So even during cloudy conditions and rainy conditions, we could gather the information about the Earth target. But nowadays, microwave is also being used in almost every sphere wherever optical has been used, and together optical and microwave are into research these days. So details on microwave, again, as I said, will be covered in a separate class. So we understood visible, visible, reflective IR, thermal IR, as well as microwave range of electromagnetic radiation. Now the next question is, how do you measure the radiation? So for that we have a branch of physics called radiometry. Radio refers to radiation, metry refers to measurement of radiation. So before I go into that, we have to understand a small concept of solid angle. Now, the angle which we are usually familiar is two-dimensional angle. How we define it as the length of the arc divided by the radius of the circle. That angle is defined in this manner. However, this in the terms of solid angle or three dimensions, we convert the circle to sphere, and the two-dimensional angle becomes the cone angle, and the length of the arc becomes the area of the circle subtended on the sphere. And so solid angle is defined as the angle, cone angle subtended by the portion of the spherical surface at the center of the sphere. So it becomes the area of the circle which is subtended on the surface of sphere, that is ds, divided by square of the radius. Okay. So in two-dimensional angle, the units are radian. In three-dimensional angle, the unit becomes T radian. So T refers to solid or 3D, right? So this is the concept of solid angle, because we are dealing with 3D objects and 3D geometry. So 2D angles will not work well. We have to switch to solid angles. So that's how we have different physical quantities that tell us about the measurement of radiation. So the basic unit is energy. The units are joules. Okay, so the amount of energy associated with the electromagnetic radiation can be measured in the form of joules. However, it does not contain any information on time, area, solid angle, wavelength, etc. So rate of change of energy. Let's slowly add this information. Rate of change of energy with respect to time, or be more precise, differential of energy with respect to time. We get radiant flux. Okay, the units are joules per second, or we call it as watt. Further, we can add the information on area. So rate of change of radiant flux with respect to area is flux density, or differential of radiant flux with respect to surface area becomes flux density. Now, depending on whether the energy was incoming or outgoing from the area under consideration, we have two nomenclatures: irradiance, when the energy is falling on the surface, and exitance, when the energy is going out from the surface, exiting from the surface. The units would be the units of flux divided by the units of surface area, which become watt per meter square. Further, we add the information on solid angle, that is rate of change of flux density per unit solid angle, or differential of flux density per unit solid angle. With respect to solid angle, this becomes radians. Okay, the units will be watt per meter square per steradian. So this is how you keep on having more information about the geometry, about time, as well as about the energy. So we started with energy, gone to radiant flux, then flux density, and then finally to radiance, where we have information on energy, time, area, and solid angle. Now coming to some laws of electromagnetic radiation. Here we switch to black body. Black body is an idealized object, as I suppose we all are aware of, which absorb and re-emit radiation in a characteristic continuous spectrum. Now, how the spectrum is dependent on wavelength is look at the curve which is shown here. On the x-axis we have wavelength, and on the y-axis we have exitance. Okay, I've termed it as spectral radiant exitance. So the units will become watt per meter square per micrometers. Okay, here we are also looking at a range of wavelengths only. So the term spectral is prefixed. Now here in this graph we observe two things. Number one, as the wavelength increases, the exitance increases, spectral exitance increases, reaches a maximum, and then starts dropping down. So this wavelength at which we have maximum exitance from the object which is radiating the energy is called peak emission wavelength or wavelength of peak emissivity. And another thing is noticeable: as we increase the temperature of the black body, the amount of spectral excitance increases at all the wavelengths. Okay, so these two things physically have been denoted in this graph, and this is called black body radiation law or black body law of electromagnetic spectrum or Planck's law. Right. So from the Planck's law, if mathematically, if we integrate it over the entire wavelength range, we get the area under the curve and we get total excitance instead of spectral excitance. We see that after integration, this total excitance is directly proportional to fourth power of absolute temperature. This law is called Stephen-Boltzmann law. That means if you double the temperature, the total excitance will become 16 times. Whereas if you differentiate this law, you will get wavelength of maximum emission is inversely proportional to absolute temperature. And this is called Wien's displacement law. But how it is relevant to the real objects? So for that, we have a figure of merit that defines how close a real object behavior is to a black body. So that quantity is known as spectral emissivity. How we define it as the spectral excitance of real object divided by the spectral excitance of a black body at a constant temperature. So we see that this spectral emissivity varies between 0 and 1. It will be 1 only for a black body. For a perfect reflector where there are no emissions, emissivity will be 0. For all other bodies, the emissivity will be varying between 0 and 1 and would be a function of wavelength. So that was about the figure of merit for real objects. Now we come to the interaction of electromagnetic radiation with matter. So we have two conditions. One is the interaction might happen at the boundary of two surfaces where the light will undergo reflection or refraction. In remote sensing, we often use the term transmission instead of refraction. So reflection and transmission, whereas within a single medium, there can be absorption or scattering. So let's see the two scenarios. One scenario is the interaction with the Earth target. The other scenario will be interaction of radiation with atmosphere. So we see that the total energy which is falling on any target gets divided into three components. The one is the reflected energy, another is the absorbed energy, and the third component is transmitted energy. So for optical remote sensing, we are more interested in the reflected energy. For thermal remote sensing, we are more interested in the absorbed energy, which will be re-emitted by the target depending on its emission characteristics. So for time being, let's restrict ourselves to optical remote sensing. That means we are more concerned with the reflections. So for that, let's see how many kinds of reflection are possible. One is specular, that means mirror-like, where Snell's law is being followed at each point, and angle of reflection is equal to angle of incidence. This is possible on smooth surfaces, whereas another kind of reflection can be diffused, where incident radiation might be in a single direction, but the reflected ones could be in any other direction. So how do we decide whether the surface will offer us specular or diffuse reflections is given by a Rayleigh criteria. Okay, so for a rough surface, if h greater than lambda by 8 cos theta, this condition is satisfied, we call the surface is rough, otherwise smooth. But what is h? H is the root mean square height variation of above a reference plane for a particular surface. Otherwise, in other words, for simplicity, you can understand it as average undulation. So there are some undulations for every surface. So if it is an averagely undulating, so you take some average undulation height that we call as h, and lambda is the wavelength, theta is the angle of incidence. If this condition is satisfied, the surface is rough, otherwise smooth. So for example, here I have considered a case for normal incidence. H I have considered to be the order of 1 micrometer, and I have considered two wavelengths where lambda A for first wavelength is 80 micrometers and lambda B is 80 nanometers. Now the surface is same, the incidence angle is the same, but wavelength is changing. So for the two scenarios, for the first scenario, you see that the surface is coming out to be smooth, whereas for the second scenario, the surface comes out as rough. So the same surface might behave as smooth or rough depending on which wavelength we are looking at. Okay. Now coming to spectral signatures, which is a very important topic. In fact, your third or fourth lecture is dedicated to this topic on spectral signatures. Now in remote sensing, every feature is identified by unique identification, and we call it as spectral signature. In case of optical remote sensing, where we are concerned with the reflectance from the target, it is spectral reflectance versus wavelength. So you see that a vegetated surface will have different spectral signatures than non-vegetated surfaces. In vegetation also, a crop will have different signatures than forest. In forest also, teak will have different signatures compared to sal, and within teak also different varieties of teak may offer different spectral signatures. The point here is every feature possible offers a unique identification in terms of spectral signatures. Now, broadly, I can tell you about what kind of spectral signatures a healthy vegetation shows, or soil shows, or water shows. These are the three major land cover types: vegetation, soil, and water. Snow and cloud also can be discussed in subsequent classes, and why and how part of spectral signatures will also be discussed, as I said, in third or fourth class. Now you can see for vegetation, the in the visible region from zero point 0.4 to zero point 0.8 micrometers, there is a bump in the green wavelength region. So why it happens is because of pigment absorption in blue and red. So more pigmentation, more absorption by the pigmentation, majorly chlorophyll, xanthophyll, beta carotene, etc., in healthy green leaves. That absorption takes place in green region also, but more absorption takes place in blue and red. So green is more reflected. Then we go to the infrared region. In the near infrared region, you can see high amount of reflectance, which is due to the physiological structure of the leaf. And then there are major dips at 1.4, 1.9, and 2.6 micrometers, which is due to water absorption dips. Similarly, you can see for soil, where you have more amount of moisture in the soil, overall reflectance is low because water absorbs in the infrared region majorly. And for water also, you can see that both types of water, clear lake water and turbid river water, offer near zero reflectance in the infrared region. The details will be discussed in the subsequent class. So the point here is every feature has a different spectral signature, which is a unique identification for it. Now coming to the interaction with atmosphere, as we discussed, there will be considering atmosphere as a single medium, which is an approximation. So there are two processes, absorption and scattering. As a result of absorption, we have something called atmospheric windows. Windows means gateways. And atmospheric windows are those spectral regions where the electromagnetic energy is passed through without much attenuation. For example, in this graph, you can see on the x-axis we have wavelength, on the y-axis we have percentage transmission. So wherever transmission is high, those shaded regions I've shown here with the purple color, and you can see that these are the spectral regions which are allowed by the atmosphere. All other portions where you have major dips, here the energy is blocked by the atmosphere, so the signals from the Earth target cannot be received both while incoming as well as outgoing radiation. The energy is blocked. So we are left only with atmospheric windows for Earth observation, Earth target observation. Also, you can see that at all the wavelengths, roughly, there is a decrease in transmission, which is not 100%. So there is some amount of absorption at all the wavelengths. So there are two manifestations of absorption. One, we are left with only atmospheric windows to make our remote sensors for Earth target observation. Second is there is a signal attenuation by the atmosphere, both while incoming as well as while outgoing. The other phenomena that happens in the atmosphere is scattering. Scattering means redirection of light. So there can be different types of scattering: Rayleigh scattering, Mie scattering, and non-selective scattering. Rayleigh and Mie together are called selective scattering because the amount of scattering depends on the wavelength. So in Rayleigh scattering, what happens is light comes, interacts with the particle. Amount of forward scattering is equal to the amount of backward scattering. Whereas in Mie scattering, amount of forward scattering is much more compared to the backward scattering. And we can see that wavelength dependency is something like lambda to the power minus 4, that is fourth power of wavelength. The Rayleigh scattering is inversely proportional to fourth power of the wavelength. Whereas in Mie scattering, this variation is roughly around lambda to the power minus 2. And in non-selective scattering, it is independent of wavelength. So for visible light, usually air molecules serve as Rayleigh scatterers. Smoke, haze particles serve as Mie scatterers. Bigger particles like dust, fog, and clouds serve as non-selective scatterers. So what is the effect of scattering on remote sensing? Due to scattering, there can be modification of incoming and outgoing radiation, both spatially as well as spectrally, right? And this might introduce haziness in the image, reduction of contrast in the image. As also, atmospheric turbulence may limit the resolution. Resolution concepts you will learn in the next class, but for now you can understand it as reduction of contrast because brighter objects may appear darker and darker objects might appear brighter due to redistribution of energy due to scattering. So this is the effect of atmosphere on remote sensing. It might attenuate the signal due to absorption. Only atmospheric windows are available, and due to scattering, there might be noise in the data. So we have learned so far in this class what, why, and how part of remote sensing. I hope you understand that. Then concepts of electromagnetic radiation, wave and particle nature, laws of radiation, and radiometry. Then we have learned how the radiation interacts with the target as well as atmosphere.